AP Cram, Calculus AB, Free Response Exam Review, Question 59, Absolute Minimum Value of a Function. Alright, so the figure shows the graph of f prime, the derivative of a twice differentiable function f, on a closed interval where x falls between and includes 0 and 8. Okay? The graph of f prime has horizontal tangent lines at x is equivalent to 1, x is equivalent to 3, and x is equivalent to 5. The areas of the regions between the graph of f prime and the x-axis are labeled in the figure. The function is defined for all real numbers and satisfies f of 8 is equivalent to 4. Our task is to determine the absolute minimum value of f on the closed interval that includes x and the endpoints 0 and 8, and then we are to justify our answer. Okay? Alright, so in flashcard set 58 of the series, we determined that we had a local minimum at x is equivalent to 6, but we had to determine minimums on an open interval, so we didn't consider the endpoints. So here, we know we have one local minimum, but now we're going to have to compare the value that we get here to the values at our endpoints, because there's a possibility that these might be minimum values also, okay? All right, so the first thing that we're going to do is determine f of 0, our starting point for our closed interval. And it's going to be f of 8, our initial condition, which we're told is equivalent to 4. And this might seem very counterintuitive to you because 8 is all the way over here. But I'm going to show you why we're doing this in a second. Plus the integral from 8 to 0 of f prime of x dx. Okay, so this usually is not seen. When we have our bounds of integration, the lower limit is usually a lesser value than the upper limit. But what we're doing here is we're going to flip the limits of integration, and in flipping them, we have to then subtract this integral instead of adding it. And so when we do that, this is what happens. All right, so we know the area under the curve is equal to our answer for integration by subtracting all this, everything, taking all this away. We're kind of sort of left with whatever falls under the curve at 0, okay? So that's why we're adding the integral from 8 to 0 of f prime of x dx, but in effect, we're actually subtracting it and taking away all this mess so that we can find out what's going on at 0. All right? So when we do that, we're left with f of 8, which we're told is equivalent to 4, minus 12, and this 12 comes from 7 plus 3, okay, which is going to be equivalent to 10. Yeah. Okay, actually, no, scratch that. We're going to have 7 minus 3, which is equivalent to 4, because this area right here falls underneath the horizontal, so it's a negative area. And then we're going to have plus 6, which you can't see because I kind of scribbled all over it. So 6 plus 4 is 10, plus this area, which is equivalent to 2. So this is how we get minus 12, okay? And then, so our final answer is going to be negative 8. So the area under the curve at 0 is like negative 8 units squared, okay? So f of 0 is negative 8. That seems pretty negative, but let's see what we have for f of 6. And remember, f of 6 was our local minimum, okay? So we're doing the same thing essentially that we did in the case of f of 0. We're going to add f of 8, and then we're going to take the integral from 8 to 6, which is this area right here, but we're going to do it in the same fashion that we did up here. So if we start off with a lower limit of integration, which is higher in magnitude than our upper limit, we can just simply flip the integral. And if you flip an integral, not necessarily flipping the integral, but if you flip the bounds of integration, you then have to change the positive sign in front of the integral to a negative sign. And we don't know our actual f prime of x function, but we do know the areas under the curve, which is synonymous with integration. So we can go ahead and substitute. So when we substitute for f of 8, we have 4, and then we have to maintain our minus sign, minus 7, because that's the area between the x values 6 and 8. Okay, and we're going backwards, so we're subtracting this area rather than adding it. And when we do that, we get a value of negative 3. So although f of 6 is a local minimum, it's not the absolute minimum on this closed interval. So far, f of 0 is our absolute minimum. But let's see what we have at f of 8. Well, we're told that f of 8 is equivalent to 4, so that's definitely not our local minimum, our absolute minimum. So our absolute minimum on the our absolute minimum value of f on the closed interval 0, 8 is going to be negative 8, and that again occurs at 0. Okay, it's kind of confusing because negative 8 and 8 are the same. So